last time was a little far out. We're going to get a little more down to earth this time. I want to try and push this analogy. We are thinking of a Turing machine as representative of a real-world computing machine, an actual computer that we use every day is, at least from an abstract point of view, more or less equivalent to a universal Turing machine. Now, our machines that we've been talking about all semester long have been phrased in terms of a machine for accepting or rejecting strings. Now, our computers, we never actually think of them in that way as a computer which takes some input and either accepts or rejects it. More often, when we're thinking of them as machines which do computations, usually we're thinking of some kind of thing where you give it some input and it tells you some kind of answer. That's what you usually think of a computing machine doing. You enter the input and then the machine gives you an answer. In that sense, we are thinking of the machine more like a function. The machine is computing the value, the answer of some function. So I want to talk about that a little bit. So this, the term for this kind of point of view is called Turing Computable Functions. So rather than thinking of a Turing machine as a thing which just simply accepts or rejects a string, you can think of it as a thing which takes some string as the input and gives you some other string as an output in the same way that a function does. So here is a definition of this concept, Turing computable functions. So I'm going to say let f be some function, be any function which takes some input string and gives some answer, right? The input is going to be a string, the output is going to be a string, but those strings, of course, they might represent numbers. But anyway, f is a function which takes some input string and gives some answer, and we say that f is Turing computable. This is the definition. The idea is Turing computable means it is a function whose computation could be done by a Turing machine. So we say f is Turing computable if there exists a Turing machine for which, if we start with x on the tape, the Turing machine halts with f of x on the tape. If that is true, then we say the function is Turing computable. It means, so this Turing machine, I mean, it is the same Turing machine, the same type of machine that we've been talking about, but this Turing machine, you're not actually thinking in terms of accepting or rejecting states. You are just thinking of, if you start with x on the tape, then the machine halts with f of x on the tape. So I'm just going to say we don't care about accepting or rejecting. We just care about what does it say on the tape when the machine stops its computation. And Turing computable means you have some function, it is Turing computable. If it is possible to make a Turing machine that when you plug some number into the Turing machine as its input string, it does a bunch of stuff and then it finishes and it has the answer f of x sitting on the tape when it finishes. All right, I would like to talk today about what kinds of functions are Turing computable. You should think what this means in a vague sense. At least to us modern people, a Turing computable function is one which you could, in theory, compute the answers with on a computer, which is to say basically anything. I mean, any mathematical function that you've ever heard of, probably its values can be computed by a computer, at least in theory. That's what Turing computable means. It means a function which, in theory, a computer could compute. But this is the technical definition. Let's do some examples. here's a very simple example of a function which we can compute on a Turing machine. So I'm going to use the alphabet A, B, and let's say f of x equals, well, f is a function which goes sigma star to sigma star. That is, the values that you plug into f are strings from A and B, and the answers you get out are also strings on A and B. And the definition of the function is this: f of x equals ax. So this just says, like in simple language, it just says stick a on the front of the string. That's what f means, right? So, for instance, f of BBAB will be ABBAB. You just insert an A at the beginning of the string. That's what f does. Okay, can you make a Turing machine which does this? By does, I mean a Turing machine where if you started with BBAB on the tape, then the machine would do some stuff and then halt with ABBAB on the tape. This is a very easy example. This is probably the easiest example that we are ever going to do of this concept. How would such a machine work? You have to imagine the head, begins pointing at BBAB. What can I do to produce this on the tape? Well, you can move to the left by one position and then write A in that position on the left and then halt. Then you will have produced this string. Let's see if we can do it. Here's our Turing machine. Can I just say in words? It must move left once, then write A, then halt, right? That's all the Turing machine is supposed to do. Can we make it do that? Yeah, I think so. Here's my starting state. All right. No matter what you see there, you should move to the left. So if it's a B or an A, I'm going to move left. So I'm going to say something like AAL, BBL, right? If you see an A, keep it A, move to left. If you see B, keep it B, move left. Or blank, I suppose. If the string begins as the empty string, you might see a blank. I'll just move to the left anyway. Actually, if it's a blank, you don't even have to move, but whatever. Then we are going to write an A and then halt. So if you move to the left at the very beginning, what you're going to be pointing at now will be blank, definitely. And I'll say blank A and then L, I guess. You have to put some direction here, although it doesn't matter. This could be a R. All right. Actually, this is it. So this says, whatever it says to begin with, move one step to the left. Then it will say blank. You change it to an A, move to the left again, or whatever. And then here, I just stop. I didn't make an accepting state. Remember, when we're talking about Turing computable functions, I don't care about anything being accepted or rejected. All that matters is that the machine halts. How do you tell the machine to halt? Well, you just run it into a dead-end state. There you go. This Turing machine computes F, and so F is Turing computable. All right. Let's do. I just want to do a bunch more examples here. What kinds of functions are Turing computable? Like I said, basically anything that can be computed by a real computer. That's what is Turing computable. Which, in a mathematical context, you should feel like means basically anything. Like, have you ever heard of some function, mathematical function, which even in theory could not be computed by a real computer? Probably you have not heard of such a thing. Although we are going to talk. There are such functions because, like I have said several times, there actually are limitations to what Turing machines can do, which means, in fact, there are mathematical functions which could never, even in principle, be programmed into a computer. Very strange, but true. We'll get to that eventually, not today. Let's try... I want to talk about, what if you want a function which takes more than one parameter? That is, more than one thing you plug in order to get the answer. This is very common in the real world. For instance, all the mathematical functions that kids know have two inputs to get an output, like the plus operation. You add two things together and get an answer. So for functions of two parameters, those are called parameters, the different things that you're plugging if you're plugging two separate things into the function. For functions of two parameters, there are a few different strategies. We could specify them with a separator in this way, if my two inputs, so for inputs, let's say I'm doing like binary Turing machine, which most of our examples are going to be zeros and ones. How about I have 0, 1, 1, 0, 1 and 1, 1, 0, 0, 1. If I have these two inputs, we could specify with a separator. You would just jam them together into one string, 0, 1, 1, 0, 1, and then put some other character, which this hash, this is what computer scientists call that, which is why it's called the hashtag, separated by this is just some other made-up character whose only purpose is to act as a separator so that you can see the difference between the two inputs. Or you could do it as another strategy is what our book calls stacked inputs, where instead of writing them one after another, this is useful if you know ahead of time your two inputs will have the same length as they do in this example. You can stack them like this. So in our book, these are written kind of like fractions, but you don't think of them like fractions. But what I'm doing is just basically writing this string on top of that string. So this 0 gets stacked with this 1. This 1 gets stacked with this 1. Then I have a 1 and a 0. That's this. Then I have a 0 and a 0. That's this. Of course, these are not fractions. You would never write fraction 1 over 0 or 0 over 0. Come on now. 1 and 0. So this is a strategy of stacking the inputs. And from a theoretical, abstract perspective, these are equivalent, because if you ever had a Turing machine which works according to separated inputs, you could always convert it into the same Turing machine but working with stacked inputs, because you can make a machine which would translate this a string that looks like this with a separator and sort of go back and forth and replace these various characters with their stacked equivalents. So these are equivalent. We're going to, in any, if I ever ask you, like, show that this or that function is Turing computable, you can assume, whenever convenient, you could either assume that it has separated inputs like this, or it has stacked inputs, whichever is more convenient for whatever problem you're looking at. Most of the ones that we're going to talk about today are more convenient for stacked inputs, and you'll see why that is. Let's do a useful sort of real-world example. This is also a very easy example, but it is very important in the real world. So let's show that this is a function called Bitwise and is Turing computable. All right. What you have to do, so this is an example. Typical, test question maybe. Show that the bitwise and is Turing computable. Your job is to make a Turing machine which computes this function. And I'm going to say, let's use stacked inputs, and you'll see why we're going to use stacked inputs. Let me tell you what bitwise and means. So the inputs are strings, binary strings. Binary meaning, zeros and ones. And this is meant to do the logical operation of and. Bitwise, I'll tell you what that means. But in order to interpret binary strings as logical, true, false, 0 is interpreted as, this is interpreted as false, and 1 is interpreted as true. And so when you do something like 0 and 1, the answer will be 0. That's because logically false and true, if you do the and operation, false and true, you get false. And is only true when both of the things are true. All right. So this is why it's called and. Bitwise and refers to matching up bit by bit. So for example, if I do the bitwise and, I'll just write and of these two strings, 0, 0, 1, 1, 1, and 1, 0, 1, 0, 1. Bitwise and means you line these up bit by bit and do the and in each position. So in the first position I have 0 and 1, that's 0. Then I have 0 and 0, that's false and false, which is false. Then I have 1 and 1, that's true and true, which is true, so that's a 1. Then I have 1 and 0, which is true and false, which is false, so that's a 0. Then I have 1 and 1, which is again 1. So this is the answer for the bitwise and. You can see why in this case it will be most convenient to write this as stacked. This is convenient to stack inputs, because now it's going to, if I stack them, it's just going to look like 0 stacked with 1, 0 stacked with 0, 1 and 1, 1 and 0, 1 and 1, right? And when you just look at one of these stacks, you have everything that you need to know in order to compute the answer here. The answer should be here 0, here 0, here 1, here 0, and 0, right? What? Copied it wrong. This 1 and 1 should have been a 1 and a 1 here. Sorry about that. Like that, right? So this is how you do bitwise, and it's easiest if you stack the inputs like this. Can we make a Turing machine that does that? So its inputs will look like that. This is the input string to our Turing machine. You need the Turing machine to start with that on the tape, and then produce this on the tape, and then halt. Let's see if we can do it. So this is a little weird. It means that our Turing machine, what it sees on the tape are things that look like this. They're little stacks of zeros and ones, and I suppose there are 4 possibilities for what that stack could look like, right? It could be 0 and 0, 1 and 0, 0 and 1, 1 and 1, right? So that's what you're going to see on the input. Let's just write out a Turing machine to do this. It's actually pretty easy. You can do this in only one state, maybe another dead-end state. Actually, you don't even need the other dead-end state, but I'll say in only one state. What's my strategy is I'm just going to look at each stack, do whatever it is. Like if it's a 0 and a 1, I change that to a 0, and then I move to the right, and I keep on doing that, the bitwise and. Check it out. This requires only one state, and if I read 0, 1, I replace it with 0, and then move to the right, right? I saw 0, 1. I replace it with a 0, and then I move to the right. And all you got to do is write down all 4 possibilities here, right? So it could have been 1, 0. What should you replace that with? If you're doing the bitwise and, this is true and false, which is false, so I replace it with a 0 and move to the right. If I had other 2 choices are 0, 0 and 1, 1, right? 0, 0, that's false and false, which is false, so I put a 0 and move to the right. 1, 1, that's true and true, which is true, so I put a 1 and move to the right. Okay, eventually you get to a blank on the end. What happens if you see a blank? Well, I didn't put any arrow for a blank, so the machine will just halt if you see a blank. And that, in fact, is exactly what we want it to do. Once you get to the end, you want the machine to halt, and this will remain sitting on the tape. So actually, that's it. That's the whole machine. That's the tweet, as they say. All right? How about, let's do a similar but more interesting bitwise operation. You could easily do the bitwise or. It would look exactly like this, only these things would be different. The answers you get, right? This would be 1, 1, 0, 1. And otherwise, exactly the same thing. We'll compute the bitwise or. Let's try a more interesting, perhaps more obviously useful function. Let's do the bitwise add. Addition, I'm talking about adding 2 numbers together. Bitwise addition. So an example of that would be something like 01001 plus 01110. All right? Where you're thinking of these as binary numbers, which you're going to add together and get another binary number for your answer. Now, what are these binary numbers in decimal? The answer is I don't really know. I think this is 9 because this is in binary. Remember, this represents 1. This is multiples of 2. This is 4. This is 8. So this is 1 multiple of 8 plus 1 multiple of 1, which is 9. This would be 8 plus 4 plus 2, which is 14. So this would be 9 plus 14, which is 25. And the answer should be whatever 25 looks like when you write it out in binary. But actually, it's not so hard to add these directly in binary. We add them up using the normal way of adding numbers together, which is Al-Khwarizmi's method. This. Write them like that, line them up, and I'm going to start over here and add them over. You just add as you normally would. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1, I got a carry here. 1 plus 1 is 2, of course, but you can't write 2 if you're writing in binary. When you want to write 2, you carry, like so. And then I go 1 plus 0, which is 1. And that's the end. This is the answer. And what is this number in binary? It's 16 plus 4 plus 2 plus 1, which is 23. What? Did I say that should be 25? 9 plus 14 is 23. Did I say 25 before? 23. All right. See, this is 9. This is 14. And the answer is 23. It really worked. Okay? This is called bitwise addition. Now, let's talk about how we're going to do this with a Turing machine. There are some important differences, but one thing I hope you will agree with is it is helpful to write the input as stacked, because when we're actually doing the procedure, we think of them as being stacked like this. So we're going to stack the input. So in this case, my input string would have looked like 0, 0, 1, 1, 0, 1, 0, 1, 1, 0. All right? This is the input string. And it's going to be kind of like our bitwise AND. The bitwise AND, you would look at each of these stacks and you just sort of do the appropriate answer each time and move yourself over to the right. One thing that you learned this when you were a kid, when you're adding in this way, you need to start on the right and make your way to the left. It's because of the way that carries go. This seems backwards to us. Actually, numbers are written this way because this way of writing numbers was really popularized by the classical Arab mathematicians. And as you know, Arabic is written right to left, which is why our numbers, in order to do this procedures based on work of the Arabs, in order to do this procedure, it is most naturally done right to left because that's the way the Arabs were used to doing things. And we still do it that way. Anyway, so this Turing machine first will move all the way to the right. Right? That's the first thing that the machine's going to do. And then it will make its way back to the left one by one stack by stack, and add things up appropriately. One thing you will notice is the answer of, like, what are you going to get from the answer of each stack? In each stack, it depends on whether you carried in the previous step. Like here, I had 1 plus 0, which is 1. 0 plus 1, which is 1. If I had had a 0 and a 0, they would add up to 0. But right here, I have a 0 and a 0, and they add up to 1. It's because of this extra carry. So we're going to move all the way to the right. We're going to have two different states. There's a carry state and a no carry state. Right? So when our computation, like in the middle of the computation, if we had no carries in the previous step, we should be in the no carry state. If we had a carry in the previous step, we should be in the carry state. And that will influence what the answer is in each step. Like here, it was 0 and 0, and you got 1. That's because we had carried from before. Anyway, let's do this. Let's write the machine. So there's actually 3 states we need. We have the carry state, the no carry state, and then there's a special state we need just to move ourselves all the way over to the right in the very beginning. So the first state is just the state which is going to move the head all the way to the right end of the string. So we have to just move to the right past anything. So if I see 0, 0, I write 0, 0 and move to the right. And you just got to do this for every possible thing. 1, 0, 1, 0, right. 0, 1, 0, 1, right. And 1, 1, 1, 1, right. Okay, this is supposed to be on a loopy edge. Sorry, I forgot to write the loop, right? We're going to stay in this state, just continually moving to the right past everything. You get to the end when you see a blank. So when we see a blank, I'm going to go blank, blank, left. And now, when you get here, this is when like the real addition is going to begin. This was just a technicality. You got to move all the way over. Okay. And then over here, I'm going to have 2 states, the carry state and the no carry state. And when we begin the computation for real on the rightmost digit, we begin with no previous carry, right? So this is I'll call it NC, the no carry state, all right? We should begin our real adding in the no carry state because in the first step, there's never a carry because there was no previous step for the carries to come from. All right, we begin in the no carry, and I'm also going to have over here, I'll write a C. That's the carry state. You know, some types of operations will cause there to be a carry in the next step, and when that happens, you got to go over to to the carry. So I just need to fill in my 4 different possible stacks, right? Here, all 4 stacks just did the same thing to get to a blank. Here, what are the 4 stacks? For instance, where does 0, 0 go? You have to think, if I add 0 plus 0, first of all, what do I get for the answer? And second of all, is there a carry? If it's 0 plus 0, the answer is 0, and there's no carry. So that means that that one goes here, 0, 0, 0. And I'm going to say L. That's because in every step after you do every one of these additions, you're going to move 1 digit to the left, 1 bit to the left. Anyway, your interpretation of this is, if I'm adding 0 plus 0 and I'm not carrying anything from the previous step, I get 0 as the answer. I move to the left and I still am not carrying anything. What about 0, 1? In this case, I get 1 for the answer and I move to the left and still I'm not carrying anything. What about 1, 0? Same. 1, 0, 1, L. And 1, 1 is the interesting one. If you add 1 plus 1, you got to think about, first of all, what should the answer be in this digit? And then, what should I carry or not in the next step? The answer is you should carry in the next step, and the answer in this digit will be 0. So this one's going to go over here. If I have 1, 1, what's the answer? I'm going to move to the left, of course. If I have 1 plus 1, the answer in this digit should be 0, and I should carry to the next. That's why the arrow is going over to the C. Excellent. What about the arrows from the C? Some of them will loop like this. Some of them will go back to the NC, which I'm going to label down below. Let's think about, first of all, 0, 0. What do you get if you add 0, 0 and you had also carried in the previous step? The answer should be 1, and you have no more carry to the next step. So then you're going to go back this way. So here I'm going to say 0, 0, 1, L. We're always going to say L because the computation always moves to the left through the digits. All right. The interpretation of this is, if we're adding 0 and 0 and we did have a carry from the previous step, the answer should be 1, and there should be no carry in the next step, which is why we go back to the no carry state. All right, I got to fill all of these in, and you just have to think this through every time. What if it's 0 and 1 and there was a carry? Then the answer should be, actually there's going to be another carry, and the answer should be a 0. So here, that one goes here, 0, 1, 0, L. All right, I put it over here because if I had 0 plus 1 and a carry from the previous step, they should add up and get 2, which means I'm going to have to write a 0 in this position and carry it into the next step. Similarly for 1, 0, you get exactly the same thing. Of course, 0 plus 1 is the same as 1 plus 0, so they should behave exactly the same as each other. And then what about 1, 1? You got to think about that. What if I'm adding 1 plus 1 and I had a carry in the previous step? That adds up to a total of 3, which would be written as a 1 in this digit plus a carry in the next digit. So that goes like this. There you go. This here is the Turing machine. Now, what are you going to, you want the thing to just halt when it gets to the leftmost end of the number. Well, when it gets to the leftmost end of the number, it will encounter a blank on the tape, and I see no outgoing arrows here with a blank, and so it will naturally just halt all by itself. So this is the Turing machine for bitwise add. All right, bitwise add is Turing computable. Tell your friends, tell your parents. It is possible to make a computer to add 2 numbers together. Yeah, everybody knows that. We just demonstrated in detail, though. All right. I would like you all to try bitwise subtraction. Can you handle it? Bitwise subtraction. See if you can do it. Bitwise subtract. And can I just say, let's just assume the answer will be positive. Just because it's a pain to deal with having to think through what exactly is going to happen if I try to subtract something which is bigger than the previous one. I don't want to get into that. So let's just assume that, you know, when you stack the inputs, the one on top is actually always bigger than the one on the bottom. Here's an example just to see if we are all thinking properly about bitwise subtraction. How about 10001 and minus 0101? 0, 1, 1. All right. Let's also assume that the two numbers naturally line up. Like they have the same number of digits, and if not, you can insert some extra zeros into the second one. Okay, how do you subtract? Well, the usual way. So 1 minus 1 is 0. What about 0 minus 1? Here, you got to borrow. And what that means is I borrow from here. You sort of take a number away from there. And this one, it's like it turns from a 0 into a 1. And then I can subtract from this one. It's kind of like puts a 1 there. Anyway, you subtract from this one and you get 1 as the answer, right? All right, now we got 0 minus 0. Now, this 0 has been borrowed already, which means actually we're going to have to make another borrow in the next part, which will convert that into something like a 1, which I can then subtract and get 1 in this digit. 1 minus 0 is 1. Then, over here, I have another 0 which has been borrowed. That's going to trigger a borrow over here, and then I'll have a 1 minus 1, which is 0. And then this is a 1, which has been borrowed, so really it's a 0. And it's a 0 minus 0, which is a 0. All right, is that correct? This, as base 10 numbers, this would be 16 and 1, which is 17. This would be 8 and 2 and 1, which is 11. And this would be 4 and 2, which is 6. So I did it right. It's a little confusing with all the borrows and whatnot. See if you can make that Turing machine. Once you make your Turing machine, how about you actually try to run it on this specific example and show me with the step-by-step on the Turing machine that this is the answer you get. See if you can make it all happen. All right, I hope you worked it out. Here's what I got. You should have begun with this move all the way to the right thing, exactly in the same way that you had in your bitwise adding machine. So this one is going to begin by moving all the way to the right. No matter what you see on the tape, you move to the right. So you got to put all these guys in. 0, 1, 0, 1, R, 1, 1, 1, 1, R. Right? And then when you see a blank, you move yourself to the left by 1 position. And now we begin the computation in earnest. The real computation, and I'm going to have 2 states. One is the borrow, one is the no borrow. We should begin in the no borrow state in the rightmost digit. This is the borrow state. I'm going to call that W for borrow. Because I don't want to use B for borrow because B already means blank, and I also don't want to use R for borrow because R already means to the right. So let's use borrow. W, and no borrow for the no borrow state. We should begin the computation in the no borrow state. And now, what do? Well, you got to think, what are the 4 possible alternatives in the no borrow, and what should the answer be? So, if I have 0 and 0, 0 minus 0, you just have to think each of these through. They are 0, 0, 1, 0, 0, 1, and 1, 1, right? If I have 0 minus 0 with no borrow, the answer is simply 0, and I still do no borrow. So this is going to say 0, 0, 0, L. The answer is 0, and I move to the left. What about 1, 0? If there was no borrow, you just do 1 minus 0, which is 1. So 1, 0, 1, L. Okay? 0, 1. If there is, actually, and this is also easy. 1, 1. If there was no borrow, then you just do 1 minus 1, which is 0. So 1, 1, 0, L. All right? This is not related to those. Okay, what about 0, 1? Here you got to do a borrow. So that's going to send us over to this state. 0, 1. When you do a borrow, this 0 becomes like a 1, and then you do 1 minus 1, and you get 0 as the answer. So you should say 0, 1, 0, L. All right? This is what you get when you borrow 0 minus 1. Okay, and now we fill in the arrows over here. From the borrow state, this is a little tricky. I think maybe the easiest one to think through is this, 1, 0. If you're subtracting 1 minus 0, but the 1 has been borrowed, then actually this is like 0 minus 0, and the answer is 0, and you have no further borrow. So that goes back this way. 1, 0, make it a 0 and L, right? If it's a 1, 0, but the 1 has been borrowed, then it's really like 0, 0, in which case the answer should be 0, and it requires no further borrow, so you go back to the no borrow state. Okay, I think the rest of them will all be over here. Let's see what we think. What if it was 0 and 0, but this 0 had been borrowed? If this 0 had been borrowed, it means we're actually going to have to do another borrow, but this will have turned into a 1, and I'll do 1 minus 0, which is 1, and then move to the left. All right? 0, 0 should have 1, and then move to the left. What about 0, 1? Again, if this 0 has been borrowed, then really it's like a 1, and we need to carry the borrow further. But anyway, it's going to be 1 minus 1 is 0. So this is going to be 0, 1, 0, L. All right? And we stay over here because if it's a 0 which got borrowed, we need to continue to borrow. This one to me is the hardest to hold in my mind, but if we have a 1, 1, but it's already been borrowed, that means it's really like 0, 1. And if it is 0 minus 1, we need to borrow again. I hope you got something like this. I hope this is right. Can we try an example? I said we should try an example. Remember, my specific example was 1, 0, 0, 0, 1 minus 0, 1, 1, 0, 1, 0, 1, 1. And the answer we got was 0, 0, 1, 1, 1. Okay, let's see if we can do this on the Turing machine. First of all, we begin in the, can I just skip the original thing which moves everything to the right? After doing all that business, it's going to look like 1, 0, 0, 1, 0, 0, 0, 1. And then we begin in the no borrow state. And we should be looking at the first digit, that is to say the rightmost digit. So I'm in the no borrow state looking at 1, 1. And according to my Turing machine, if you're in the no borrow looking at 1, 1, you make this a 0, move to the left, and stay in the no borrow state. So it should be 1, 0, 0, 1, 0, 0. Stay in the no borrow and move to the left. And this 1, 1 has been turned into a 0. This is what I see on the tape after the first step. All right, let's keep going. 1, 0, 0, 1. Okay, now we moved this one, moved to the left and stayed, switched into the borrow state. So now it should say W, 0, 0. This 0, 1 has become a 0. No, a 1. Right? From the no borrow state, if you see 0, 1, it becomes a 1. And then a 0. All right? Okay, look on your Turing machine. What do you do in the borrow state from a 0, 0? The answer is you stay in the borrow state, you make it a 1. So this now becomes 1, 0. Stay in the borrow state, move to the left. Make this digit now becomes 1. And then we have 1, 0 from before. All right, almost done here. In the borrow state, if I see 0, 1, I stay in the borrow state and make that a 0. So I'm still in the borrow. This becomes a 0, 1, 1, 0. All right? And then W. In the borrow state, if I see 1, 0, it goes back to the no borrow state and becomes a 0. So this now says no borrow. I guess it moves to the left again, so there will be a blank here, but then a 0, 0, 1, 1, 0. And this halts because there's no outgoing arrow from the no borrow state with a blank, and so the tape says at the end 0, 0, 1, 1, 0. I mean, there's a blank here, but we don't care about that. That's the answer, isn't it? That's how we do bitwise subtraction. This is a Turing computable function. Believe it.